Okay, so thank you again, everyone, for joining us. We are here with Steve Mann from the Passive House Network and Home Energy Services to talk about Passive House retrofits. I've started recording this course, which will be posted to our on-demand page. Um, and before we get going, we have a lot of content in today's course, so I'm going to be kind of breezing through our slides, but I just have a few to run through. So as always, please make sure that you're on mute throughout the duration of the course. If you'd like to ask a question, please add it into the chat or feel free to raise your hand and we'll call on you to unmute yourself. So just a little bit about us really quick. We are the Tri-County Regional Energy Network, also known as 3C-REN. We're a collaborative partnership between the counties of San Luis Obispo, Santa Barbara, and Ventura, working to improve energy efficiency in our region by offering free programs and services for building professionals and households. And we currently have 3 programs. The first of which is our Energy Code Connect program, which offers free trainings and support to make the energy code easier to follow. And we have our Energy Code Coach service, which is an over-the-phone, online, and in-the-field support for Title 24, Part 6, and Part 11 questions. And then our next program is our Building Performance Training, which serves building professionals. And that's what this course is brought to you through. And then our third program is our Home Energy Savings program, which incentivizes contractors and helps residents save money and make their homes healthier. And then the next slide, just really quick. Usually I have this slide at the end, but again, I kind of want to leave as much time for Steve to present all of the content today. So I'm running through these in the beginning. But again, we have our free Energy Code Coach service. I have the web form link, and then we have our hotline phone number there for you. It's for residential, non-residential questions to help you get through projects and be compliant with the energy code. And then we have 2 AIA learning units for today's course that have been approved. And then we also have actually quite a bit of passive house courses coming up. I've kind of pulled those ones out of our live catalog and added them here. One that I especially want to plug is the September 30th course. It's a hands-on in-person training in San Luis Obispo. It's going to be at the People Self-Help Housing, and it is the Passive Design and Build Bootcamp. I have a flyer for that. I'm going to add that into the chat box so that there's more information for those that are interested. And with that, I'll hand things over to Steve.
Great, Sarah. Thanks very much. Can you hear me okay?
Yes.
Good. Okay. And I would actually put in a plug too for the boot camp. September 5th is like an introductory session. September 30th is a 5-day hands-on passive house certified tradesperson training for those of you that are interested in getting your hands dirty with actually touching building components and assemblies and things like that. It's the only course of its kind in the United States, and it's good. It's very good. It's done by EV Systems, so I just give a shout out to them. Okay, onward. We're going to talk about passive house retrofits. In this case, these are retrofits in the context of a design process and a certification process that's designed by the Passive House Institute in Darmstadt, Germany. It's called the EnerPHit standard. Okay, not to be confused with retrofit standards by Passive House Institute US. That's a different process, a different protocol, a different program. They're both good, but we're just going to talk about the German version of it today. A little commercial for the Passive House Network. It's a North American organization, primarily United States, but we also do work with folks in Canada a bit. The Passive House Network's primary goal and mission is education and training and building awareness about the Passive House Institute process and certification process and design process. We have conferences every year. We have trainings like this ongoing all the time. There are 6 regional chapters listed here on your screen. And there are, in addition to the chapters, there are affiliates. And I'll put a plug in here for Passive House California, which is an affiliate of the Passive House Network. The difference is, a contractual difference, but essentially the affiliates and the chapters do the same kinds of things. Again, regional events, so on and so forth. The Passive House Network also is affiliated with the Passive House Institute, shown on the bottom. In conjunction with them, there is the International Passive House Association, which is an educational arm of the Passive House Institute. There is the North American Certifiers Circle, which is a group of people that certify passive house buildings, and I'm a member of that. I do certifications, among other things. And there are different types of certifications you can get. One is the Certified Passive House Designer, which there's a California cohort going right now as we speak. There's the tradesperson, which is the EMU training, which Sarah and I just talked about a few minutes ago. And then there are certified building. Okay, so lots of different ways to sort of dip your toe into these waters. This is me. I'm based out of Berkeley. I'm a self-employed consultant. I've done a lot of green sustainability stuff over the last 20 years, and a bunch of them are listed here. Right now, I just basically do 100% passive house consulting and training and certification. And I'll do a little bit of Title 24 stuff too for my passive house clients, but that's not my focus. Long time owner, designer, builder for about 30, 35 years. And relevant to this content of this course, my first 5 or 6 projects in California were gut renovations. Unfortunately, for the first few of them, I really didn't know about passive house. Although I was leaning in that direction already, I just didn't know it. And then as things developed, I became more and more drank the Kool-Aid of passive house world, starting back in about 2005. And I've been doing hardcore passive house stuff for about 15 years now. My last 2 projects were owner, designer, build, canoe construction projects, both passive house certified and LEED Platinum certified. So that's kind of where I come from. Here is the course description. Now I'm going to go pretty fast because this course was really apparently designed for 2.5 hours. I didn't design it, so I can't take any credit or any blame for that. It is what it is. So I'm going to go pretty fast and hopefully leave time for questions at the end. I find that this can trigger a lot of questions, especially if there are folks of you in attendance that have specific renovation projects in mind and you have burning questions. You want to know how to accomplish something related to a specific project. So as we go along, throw your questions in the chat. Don't be shy. I'll try and answer them as they come up. But if I miss one towards the end, when we hopefully have a little time, please bring them back up again in case I just in the frenzy of getting this done, I missed something. I'm not going to read all of this verbiage. Essentially, we're going to talk about the EnerPHit process. That's the retrofit process defined by the Passive House Institute. I'm going to talk about some of the history. I'm going to talk about the different ways you certify in the EnerPHit process. I'm going to do some case studies. I'm going to talk about some pilot programs that are going on. It's just a whole bunch of different things related to passive house specific retrofits. You will get the slides so you can come back and reread this stuff at your leisure. Here's the agenda. Okay, I think we just did the orientation. I'm going to do 2 minutes worth about passive house in general and then EnerPHit specifically. Talk about the 2 EnerPHit methods. There are 2 different ways you can qualify a building, assuming you want to certify it. I'm going to talk about some of the more nerdy details of what's involved in passive house in general and EnerPHit specifically. I'm not going to do a deep dive in the nerdy stuff. I'm just going to show you just enough to, if you have a tendency to lean towards the nerd world, just enough to whet your appetite so that you'll say, oh, this looks interesting. I should learn more about this stuff. Talk about some exemptions for the program. There are a few exemptions with pretty much everything in the world. It's the answer to all questions is, well, it depends. Well, that's true in the EnerPHit world as too. It depends. Some things do depend on other things. Okay. I mentioned the pilot programs, and then I'm going to talk about 3 case studies with pictures and talking about specifics about how you put buildings together or take them apart and put them back together. Unfortunately, none of our case studies are based in California because we had very few EnerPHit, certified EnerPHit projects in California. We need more. We have to have more with the current climate situation we have going. We need to retrofit lots and lots of buildings. So hopefully you'll find this interesting. You'll want to go forth and start doing retrofits in this kind of context and become part of the climate solution process even more so than you probably are now already. Since you're here, I'm assuming that this is already on your radar. So, okay, let's talk about the standard. It comes from Germany, and the founder of the Passive House Institute pretty much said, in terms of, well, he calls this a structural intervention, which is a German way, or that's his way. He's a fabulous guy, but it's his way of saying, yeah, if you're going to retrofit a building, okay, if you're going to do it, you should do it properly. And when they decided to develop this program, they decided, well, we have to define the way to do this. So if you retrofit a building according to these criteria, you're going to do it properly. And that means that 2 things really. It means that you retrofit the building so that you achieve what you want to achieve. And I'll talk about what we want to achieve in a minute. And then you also do it in such a sequence, because retrofits don't all happen in one big lump typically. Well, they might not. So they assume that there might be cases where you want to retrofit in stages. And that introduces some interesting situations that in the passive house world you need to be aware of. Okay. So we'll dig into all of that stuff. The point of this slide is to just say, yes, retrofitting applies to any kind of building from small to very large. And the principles are the same. The way it's actually achieved might differ from building type to building type, but the end result that you want to achieve is pretty much identical. Now, here's just a couple more examples. Specifically, here's the upper left. It's a grocery store. Bottom left is a garment factory in Sri Lanka, which is hot and very hot and very humid. And on the right is a university building in Cambridge in the UK. So just a few more examples. Retrofitting in the passive house world can apply to any type of building. That's the message. Okay, let's talk about passive house, which sort of sets the stage. There are a bunch of goals we want to achieve. There's a stereotype that in the passive house world, the primary goal is to save energy. That's actually not the primary goal, although it's listed first here. It should be last on this list. The primary goals are occupant comfort, which has to do with just temperatures. Indoor air quality, you want excellent indoor air quality. You want the building to be so durable that it can last for decades, perhaps even a couple of 100 years. And you want it to be resilient. And then finally, if you achieve all those goals, what comes out of that actually is low operational energy. That's like a side effect. That's not the primary goal. That just happens naturally if you achieve these other types of things. Okay. There are 5 basic principles that we look at. One is, and I'm going clockwise from the bottom left on the picture on the right-hand side. First is thermal insulation. We want to have the right amount of insulation around the whole building. On the outside, could be on the inside, but we want to create basically a cocoon. Or another analogy you like to say is, a nice warm coat that's suitable for all climate conditions for the location you're in. Next up is passive house windows. Well, they don't have to be passive house windows. They can be any good quality window. And they do not have to be triple pane windows, which is another stereotype. Double pane windows are possible in many parts of California because we have a mild climate in many locations. But what you want good performing windows that are properly specified for the project and the project location. Third, up on the top is adequate ventilation strategy. And this comes out of actually the fourth item. But I'll talk about that. I'm getting ahead of myself. In a passive house building, you want to have, you notice on the left, we say good indoor air quality. The only way you really achieve that is to have a continuously operating ventilation system that brings in filtered fresh air and extracts overly humid or low quality air from the house. So you bring in a number of cubic feet per minute and you extract the same amount of cubic feet per minute. So you have a balanced ventilation system that keeps the inside of the house, keeps the air quality very good. Now, if we look over to the right, the fourth item is air tightness. This is really the primary achievement of the passive house world, is to build airtight buildings. I tell my clients, you want to think of this as you're building a balloon with no holes in it. And then if we look at the first thing, the thermal insulation, I say, okay, you build a balloon and then you want to make it a well-insulated balloon. This is what we're doing. This is kind of an easy way to think about this. Airtightness is the scariest thing for most new contractors or tradespeople that have ever done one of these before. It's totally achievable by people that have never built a passive house building before or retrofit one. You just need to understand some of the building science and how you achieve it and different ways you can go about doing this. Okay. And then finally, the fifth principle is thermal bridging. You want to eliminate or reduce significantly thermal bridges. A thermal bridge is a location in a building where you have unwanted thermal energy movement. Now, that can be either heat or cold moving from inside to outside or vice versa. In the wintertime, you don't want the heat to escape. In the summertime, you don't want the heat to come into the building. Okay. So it's just thermal energy movement, depending on the time of the year and the climate conditions. You want to minimize that as much as possible. Now, that achieves a couple of things. It lowers your operational energy, but it also helps guarantee that you have a low moisture risk. We evaluate these things. And if you have those things, then you have a resilient building. So all of these things kind of work in a synergy to achieve the goals that we're trying to achieve. I'm going to talk about all of these a bit more as we go on. Okay, this is for passive house new construction. This is one of the nerdy slides. We have very specific numbers we have to hit, okay, in order to certify a building. And I'm not going to talk about these in great detail. I'm just going to say these numbers are tough to achieve, okay? They fall into the areas of heating, cooling, and air tightness, and primary energy, which is the amount of energy consumed by the building to run the building, okay? If you look at something like heating demand, and here we have 4.75 kBTUs per square foot per year, you don't need to remember that. That heating demand, that's the amount of energy the building consumes in a year. And that's typically about 75 to 90% less than a code built building. That's a pretty tough criteria to hit, but it's totally doable. Okay. Same kind of thing in cooling. Again, it's 4.75 with a fudge factor for dehumidification if needed. Again, you have to hit that. You can't be greater than that energy consumption. The tough one is the air tightness. It's 0.6 for new construction again. Now, 0.6 is 1/10, approximately 1/10 of the current criteria for a new single-family residential building in California under Title 24. Same thing for multifamily. So this is why it's scary. That's a really tight building. You really are trying to build a balloon. It's not a perfect balloon, but it's as perfect as you can get it. And for instance, in my house, when we certified it, our final blower door number was a 0.43. And the builder who had never built one of those was delighted and amazed. And so was his crew when we did our blower door testing for the first time. They were like, oh my God, this is actually possible. We can do this, and now we know how to do it. And it's a big moment because that's a really tight building. Okay. Totally achievable. So the question comes, if you're going to tear a building apart, why not just do passive? Why not just do this? Well, the problem is that you run into things from existing building situations that you have no control over. And here's just a couple of examples. The building's already been designed and built, and it's sitting in a location. Now, one reason why you can build a passive house building is because if it's new construction, you have control over the orientation and the siding and how it sits in the landscape and how the shading is affecting the performance of the building and where you put the windows and where you don't put the windows and things like that. It's an existing building, that's out of your control. Even more so, if you look at the slide in the middle of the picture in the middle, that's a brick wall, I believe, or I guess it's brick, and we'll have more close-ups of that later. If you need to build a balloon, it's really hard to build a balloon out of a brick wall, especially an old brick wall. Uh, so you have some real interesting challenges there, and we'll look about that even more later on in one of the case studies. Uh, on the right-hand side, this is thermal bridging. This shows concrete wall and footer and slab situation. Now, you may not be able to excavate around the whole building or tear up the existing slab if there is one, or insulate the footer or things like this. So you may not be able to control the thermal bridging in all cases. Um, we'll see some interesting, in one of the case studies, again, some interesting ways they dealt with those issues. But this can be tough. You can't always manage that. So what happened is the Passive House Institute said, oh, okay, well, we need to be a little bit more flexible when we're talking about retrofits. So they defined the EnerPHit standard. These are the two tight areas. The air tightness is thermal bridge free. Possible to replace windows. It's possible to put continuous insulation on. It's possible to do mechanical ventilation with heat recovery. So 3 out of the 5 are pretty easily achievable. 2 out of the 5 might be difficult. So the passive house world was created about 30 years ago. This is back in, I think, 1990, roughly around there, somewhere in that time frame. And so they did passive house new construction for, 10 or 15 years. And they said, okay, what about retrofits? And so they did the first pilot project for retrofits in 2010. The building on the left was the first one they did. And they pretty much insulated the roof, the walls, they replaced the windows, they put in ventilation, they put in a high efficiency condensing boiler, they put in solar collection, okay, solar PV, and a hot water recovery, drain water heat recovery. Renovation costs here, it's in European units, it's 510 euros per square meter. That equates to roughly about $150 per square foot, roughly. Okay, don't check my math on that. That's in the ballpark. And what they found was they achieved all the goals they wanted to achieve. And also the operational energy of the building went down by 85%. So you reduce the utility bills 85%. Everybody's now comfortable. The air quality is good. The building has been made over so that it has now a lifetime of maybe 100 years, maybe 150 years. Whereas otherwise, this wasn't done at some point, maybe it would have been torn down and replaced, which is kind of what we do here in North America in a lot of cases. Okay. Then the picture on the right shows, I think this was the second pilot they did on the single family residence. Same thing, same approach applied, and they managed to achieve the same kinds of results. So this is where this all started back around 2010. This is actually not, well, it is a retrofit technically, okay, because this was an existing house in Santa Cruz, and they did tear it apart and put it back together, but they did it in such a fashion that they were actually to certify it as new construction. They met the metrics for new construction, even though it's a retrofit. So it's kind of this is the first one in California that was actually a retrofit, but technically it was treated as a certified new construction build. So it's one of those hybrids that, it's a little bit of this, a little bit of that. Okay. But anyway, you can see on the right, okay, there's the energy reduction before and after. The gray is before, the green is after. And if you Google Midori House in Santa Cruz, as it's spelled like there, I believe they still have an online blog. And this is a couple, and the woman in the couple actually wrote a book about this. very interesting sort of extended case study about how they did in the decision-making processes and the challenges and how they overcame the problems and so on and so forth, and about the team effort and everything else. So I'd recommend you go ahead and take a look at that if you can find it. Okay, so if you're interested in doing this and trying to figure out if you may want to retrofit a building, this is the primary document you want to look at. Okay, it's the certification criteria. This is nerdy, um, and this talks about EnerPHits and also low energy buildings, which is yet a third standard that's part of the passive house world. Excuse me. And this lays out the criteria, which I'm going to touch on. I think it's about 20 or 25 pages. Oh, this is the long version. On the bottom there, it says 135 pages. Uh, there is a shorter version of this, is about 20 or 30. So, like I said, if you really want to nerd out, there's plenty of information here. Okay, but that's the place to start. And talk to a certified passive house consultant or designer or certifier and sort of say, okay, I've got this building. I'd like to retrofit it. Here's kind of sort of what its situation is. Do you think that's possible? If so, how do we go about achieving that? And does that make sense? Um, you can start the conversation at a very non-nerdy level, but eventually somebody is going to start digging into the numbers because there's a very scientific approach to doing buildings. That's why it works. There are advanced classes. Now, this is not educational classes. These are levels of certification. I'm not going to dwell on this too much. This is true for new construction and EnerPHits. See the new construction on the top row with the red banners and then the yellow banners of the EnerPHits. The difference is at the basic level on the left, you get a certified building. As you go towards the right, it just means you put more solar PV on the building. So you're pulling less energy from the grid. The less energy you pull from the grid, the more the building is self-sustaining, the less impact you have on climate change. Essentially, that's the simplification, but that's the underlying logic there. Okay. Okay. Let me just take a quick drink of water before my throat gives out. All right. I don't see any questions yet, so that's good. I'll keep plugging along. There are two methods. You want to certify a building as a certified retrofit. The two methods are either the heating energy demand method or the building component method. And then within those two methods, there are the three classes I talked about, where you have more PV towards the right. And then in addition to these two methods, there's some general criteria that applies to both methods. Okay, and I'll dig into all of this stuff a little bit more. The energy demand method is basically a calculation. We use a piece of software called the Passive House Planning Package. And what you do is certified passive house designer or consultant, or anybody, they don't have to be a certified anything if they know how to use this software, builds a model of the building in the passive house planning package, does the calculations to determine if certain heating and cooling and renewable energy criteria are being met. And if so, then the building can be certified. The other method is, instead of doing the calculations, although you still use the passive house planning package, but in a different way, a simplified way. It basically, there are a list of thresholds you have to meet for different building components, like let's say insulation values in different locations, window values, ventilation values, so on and so forth. And I'll show you a few examples of this. So you can take either approach. And they're both viable approaches. Depending on the situation, one might be easier than the other. So this is why it often makes sense to get a certified passive house designer or consultant involved early on to determine what might make the most sense. Regardless of the method, and remember I said there's some general criteria. There's some of the general criteria, okay? Basically, there is still an airtightness threshold, but instead of 0.6 for new construction, it's 1. And I didn't really explain what that number means. That's air changes per hour, okay? I'll show you how that testing is done in a few minutes. Um, just know that it's essentially the number of cubic feet per hour that can be moved in and out of the building under normal conditions. Okay. Uh, not when not when any equipment is running or any testing is being done, but the house is sitting there in Mother Nature, and under climate conditions and wind conditions and site conditions, the building does not leak energy in or out any more than can be done with that many air changes per hour. Okay. Um, so that's the primary alternate criteria. The air tightness is a little more flexible. The other thing that's a little more flexible is the primary energy. Again, that's the amount of energy that you consume from the grid. Okay, this is not the amount of energy that's used by the building directly, by your heating and your cooling, your air conditioning, all of that stuff. This is how much energy you're theoretically pulling from the grid, uh, from the power plants that are providing that energy. Okay. We had questions on about that last time I did this. And if anybody has questions about site versus source energy, we can talk about that a little bit. Here we're talking about source energy. Okay. So the other thing we look at is we look at moisture management. Okay, and that's basically we don't want any part of the building on the inside to have the ability to develop condensation or moisture or mold or mildew. This is how we make sure we have a durable building and that the air quality is maintained. And we looked at parts of the building specifically uh, looking for potential moisture problems. Okay. And this is done regardless of the type of EnerPHit, and this is done in new construction as well. And then the other thing is the window thermal comfort, which I'll describe in a minute. We want to make sure that that's maintained. Here's just the benefit of the air tightness. If you look at the chart on the left, on the vertical axis, it shows building heat loss. That can also be building cooling loss, depending on the time of the year. It's thermal energy movement in and out of the building. Okay. On the passive house, uh, number 0.6, that's on the far left. That has the lowest building heat loss. The EnerPHit is a little bit to the right of that, okay? And then you see as you go up towards the right, you see the 0.3 number there. Well, California is actually for new construction, single family, it's at about 0.5, so it's up here. Multifamily is at about 0.7, which is up here. So you can see just by increasing the air tightness, you radically decrease the heat loss or the energy loss. Okay. So this is why air tightness is really, I think of this as the superpower in the passive house world. If you can achieve this and nothing else on a retrofit, you've done a great job of radically improving the quality of the building and the reducing the energy consumption and reducing the impact on climate change. Okay. This is how we do this testing. There's this red thing on the right. This is a blower door. Okay. And basically what we do is we close up the building. We create our balloon in theory. We hopefully have created a balloon. And then we put this thing in the doorway and we turn the fan on. And with the fan, and there's a piece of equipment that's not shown that's hooked up to it called a manometer. And it can measure how much air is moving through the fan. And from that, we can determine the air changes per hour number for that building based on the volume of the building. That's how we determine how airtight it is. Very simple test. It can be done in 10 or 15 minutes. What we find in the passive house world is we do this test multiple times because you want to make sure that once you start tearing a building apart in the retrofit world and you start building your balloon, you want to test the effectiveness of how well you're building that balloon. And the only way you can do that is by doing blower door testing. And typically, in a retrofit, I encourage my clients to do this at regular stages. I actually encourage my builders and my architect clients to actually buy this because it's probably about $3,000 at current rates, and you can just have it there all the time and test as much as you want. You don't have to hire somebody to come out and do your testing for you. And it's a great way to figure out how these buildings work. Highly recommend it. Now, in the EnerPHit world, in addition to hitting that metric of 1 air changes per hour, there is a mandatory leak detection. So basically, when you set up to do this test, and there's a final version of this, this is like, the grand finale. You do this test, and regardless of whether you hit the number 1.0 or 0.6 or whatever, you're supposed to go and do mandatory leak detection. That basically says, okay, well, we got our air changes per hour number, but we're also going to go and look to see if we can find any other leaks to get it even lower. Okay, and you have to do this as part of the process. And then the builder or the third party doing the testing has to file a document with the certification people that says, okay, yes, I confirm that, yes, we got the blower door test and here's our number. And by the way, we also went and did this additional leak detection. Okay. And we looked at all the spots that were prone to leakage. And once you do this for a while, there are certain places that are more prone to leakage than others. And so you check those definitely for sure. And you look to see if you can find any other leaks. And if you can, you see if you're able to fix them or eliminate them. And so this is just going one additional step to make your result even better. This is required as part of the process too. Okay, so that's the airtightness process. Let's talk about moisture resistance. I'm going to check our time here. Let's see how we're doing. We're doing okay, I believe. I can find my clock. I don't see my clock. Okay, that's all right. We'll just keep going.
Steve,
Yeah.
it's 10:08.
10:08. Okay, good. I think we're doing all right. Thank you, sir.
Sure.
Okay. All right, moisture resistance. We have this number we calculate for moisture resistance. And don't worry about how it's calculated. What it is, it's a measure, it's a way we measure a location inside a building to determine if there's a risk for moisture buildup there. If you have moisture buildup, you can have mold, mildew, condensation. We don't want this, okay? This is dependent on the climate zone. And so you can see the chart for the specific number for each climate zone. Now, with the latest version of the Passive House Planning Package, this chart on the right is no longer quite this rigid. What they do is they actually calculate this threshold that you have to be above. The higher the number, the lower the moisture risk. You have to be above this number based on the climate in the specific location of the building. Okay, this is a good set of guidelines for giving an idea of what those numbers should be in various locations, but it's going to be more specific. It's project dependent in the new Passive House world. The way this is done is we run software called finite element analysis software, and this is especially in the Passive House world. And basically, you take a location that looks like it might be at risk for moisture damage, and you build a little model of it. And this is different from the Passive House Planning Package model. This is different software, and you calculate this number. And here you can see on the right, this is kind of fuzzy, but here it shows that for this location inside this building at this corner, where the wall and the floor come together, the FRSI number is 0.854. And down below, where the basement wall meets the floor, it's 0.888. So regardless of the climate zone on the right, these are good numbers. So this assembly, this building assembly at this intersection has no risk for moisture damage or mold or mildew or anything else or condensation. So that's a good thing, all right? Then we have this other thing we look at called a psi value. Now this is related to moisture, to the FRSI numbers, but it's different. This is actually a calculation of the thermal bridge at this location. Thermal bridges and FRSI numbers kind of go hand in hand. If you have the potential for a thermal bridge, that's an indication that you've got a location where you want to look at the FRSI. Okay, but you could have a thermal bridge, but have an acceptable FRSI number. Okay, they don't necessarily both have to be perfect or suitable or appropriate. You can have a thermal bridge but have a good FRSI number. You could have pretty much no thermal bridge, but have an unsuitable FRSI number. Okay. Um, and that's something as you dig into this stuff, you just learn about this more. I just want to give you a flavor for this. We calculate this number, the FRSI, I'm sorry, the psi value down here with the same software, but it's a different calculation. And notice it's a different location. It's outside. So what we're looking at here is the thermal energy transfer at this point. This is considered the weakest point of this assembly right here. And the software figures out what that is, or the person doing the analysis picks that point and says, okay, tell me what the psi value is at that location, because they just know that's the weakest point. And we're trying to identify thermal transfer through this intersection, unwanted thermal transfer. All right. So that's what we're looking for there. For FRSI numbers, we're looking for moisture possibility on the inside surfaces. Okay. In the passive house planning package, there is a threshold that's calculated, and that's for this project. Remember, I said this chart is a good starting point, but in the new world that we're in, it's project specific. So in this project specifically, the FRSI number has to be greater than 0.45. The passive house planning package has a dashboard that shows you overall how this project is doing. And notice here's your heating, and here's your cooling, and here's your air tightness, here's your moisture protection, okay? And here's your thermal comfort, which we're going to talk about in a minute. So the dashboard shows you everything. One of those things happened to be moisture protection. And if you get all green yeses over here, that means the building can be certified. Or if it's finished and the software reflects the finished conditions and you get all green yeses, it means the building should be certified and can be certified. Okay. Now the FRSI number in retrofit, you can have constraints. And one of the biggest ones you can have is, well, where to put the insulation? Because you may or may not be able to, let's say, tear the building apart from the inside or tear it apart from the outside. And you don't know until you start digging into the project. There are a lot of reasons why you can't insulate on the outside, although you may want to. And we'll look at some case studies. So where you put the insulation makes a big difference on many things. One of those being the FRSI number. And so on retrofits, we pay very close attention to this because the insulation has a big effect on it. Now, if we look at these two cases, on the left, the insulation is on the inside. Okay. And in these kinds of pictures, this is just another finite analysis software picture that you get where it shows temperatures. Okay. And the redder the numbers, the higher the temperatures. Again, that's a simplification, but that's kind of it. So you want as much red on the inside as you can get, because that means that there's no cold spots. On the left-hand side, with the insulation on the inside, at that location, the FRSI number is 0.554, which may be too low. It may be lower than you want, depending on the climate and the project. The situation on the right, the insulation is on the outside. And the FRSI number with that assembly is 0.911, which is going to be great regardless of the climate zone, except maybe in Antarctica. I don't know. I have to see the modeling software and the outcome of all that stuff. So in a retrofit, where you put the insulation is a big question. And this is one reason why. If you have the insulation on the inside, there are ways to mitigate those potential problems, that low FRSI number. For instance, here's one particular approach you might take, and this is where you end up getting a consultant involved early and somebody who knows how to do this kind of calculation early on, because you need, before you even start tearing the building apart, you should be looking at this junction and determining if you have a problem or not. So in this particular case, one possible solution is adding some insulation on the inside underneath the floor assembly. And you can see on the right, that raises the FRSI number a bit. Okay, it raises it from 0.554 to 0.606. Well, that's better, but if it was my building, I'd want it to be even better than that. And this is ignoring the whole question of, well, if you've got insulation glued on the wall or the ceiling there, how do you deal with that architecturally? Is that in a basement? If that's in a space that people actually use regularly, that's you're going to have to do something with that aesthetically. So oftentimes when the retrofits, we have to look at these junctions early on to figure out how we're gonna deal with them. And this is true. Intersections between walls and floors are big points, but even more problematic or more difficult to deal with are going to be intersections between floors and foundations, walls and foundations, walls and roof lines. Okay, those are the critical places that we have to be looking at. So, and this is the kind of analysis we need to do in those spots. Okay, so that's a little bit about FRSI. That's a little bit about psi values, which I'll talk about some more. Let's talk about the comfort criteria. Now, remember, the primary reason we build these buildings is because we want to create um, uh, a situation that the occupants are very happy with. We want them to be comfortable all the time. We want them to have good air quality all the time. We want them to be happy, essentially, to boil it and simplify it. One way that people are unhappy in cooling climates or in heating climates is if they stand next to a window or in the vicinity of a window, the temperature of that window or coming through that window is very different from the temperature that we want on the inside of the building. And in the wintertime, typically we're looking at about 60 to 70 degrees. And in summertime, we really don't want to be any higher than about 77 degrees. Those are passive house threshold. Other systems or other values, let's say like ASHRAE or ISO or something like that, might have different comfort criteria. These are passive house comfort criteria. So what we need to do is, in order for the windows not to be a problem, is we want to make sure that the temperature of the window is within about 5 degrees of the interior temperature. Now, depending on how you calculate this and how you look at it, it might be 4 degrees, it might be 6 degrees, depends on the climate zone and again, the project and everything else. But we're looking for something in that range. Anything greater than about 5 degrees, the person standing in the vicinity of the window is going to feel colder. If it's like on the picture on the right, the window is 5 or let's say 6 or 7 degrees less than our interior temperature. Or summertime, if it's say 6 or 7 degrees warmer than our threshold temperature, they're going to feel that they're going to be uncomfortable. They're not going to like their where they're living. But we want to make sure that we avoid those issues. And again, here's a different definition of that. And notice it's here it says 7.6 degrees below the operative indoor temperature. This is, like I said, there are multiple definitions of this, but notice this one's still about 5 degrees. Okay, so every time I see criteria in this area, I see a different set of numbers. Okay, notice that the passive house planning package calculates the actual thresholds, and I'll show you that in a few minutes. And it hides a lot of the complexity of the calculation. All right. What you need to know is that you just want to make sure that the windows are of sufficient quality so that you do not have a significant temperature difference between inside and outside. This is what it looks like in the passive house planning package, okay, which is a big spreadsheet. For those that you don't know, it's a really big spreadsheet with about 40 tabs in it, okay? This is just a portion of it. And here you can see this is the exterior temperature. They're assuming this is the worst case exterior temperature. So that's the threshold that they use to determine the window comfort criteria. So the question is, well, how do they do that? Well, we actually, when the passive house planning package calculates what a window is doing, we look at all the individual components of the window. And here from left to right, we look at the U value of the glass. For those of you that don't know what U value is, it's the inverse of the resistance, which you probably all know. That's the ability of a material to resist thermal energy transfer. Okay. So in this case, the U value is the ability of a material to transmit energy through it. Okay. We use the U value to make the math work out. Again, that's a gross simplification, but I don't want to dig into that anymore. If you want to know more about this stuff, take the Passive House, the certified designer, our consultant training. We spend a lot of time on this stuff. Okay. Anyway, we look at the U value of the glass. We look at the U value of the frame. We look at the psi value. And remember psi value, that's the little triangle, the trident thing. That's the psi value of the intersection between the glass and the frame. And I'm not going to say why we talk about psi value there, other than it's not an area, it's a linear calculation. Then we also look at the psi value of where the window is installed in the assembly. So in order to calculate that, you need to know what it's assembled into, what it's installed into. So you need to know what the wall or the roof for a skylight looks like. You take all those things, you multiply them all out, you add them all up, you divide it by the area of the window, and we get this thing called the UW installed value. That's the overall U value of the window assembly in the building assembly that it's installed in. And you'll notice on the left, we have kind of like a threshold that we need to meet depending on the climate zone. Okay, and again, this is sort of a guideline chart, but again, the UW installed threshold is project specific. This is kind of like this sort of guidance. So if you're doing one of these projects and you're in a warm climate zone and you find that your UW installed value just in general is going to be, let's say, 0.30, that's higher than you want it. You need to have it lower. Okay. So this is just a way to kind of alert you. But what actually happened is in the Passive House planning package, it looks at this for every window. And notice here, this is for a vertical window here. It says 0.18, and over here, this 0.18 is for the UW installed value. So this implies that this project is in a warm temperate climate. Now you don't know that for sure because it depends on the project. This is a project specific number, but it kind of suggests that. What's more important is that's kind of the threshold for this project. That's the exterior temperature. And we calculate a UW install value for each window. Now notice that this number says 0.18 is your threshold, recommended threshold, and all of these are greater than that. What happens is there are exemptions depending on the size of the window. And so in this case, these two windows are smaller than the Passive House planning package and the Passive House process cares about. They're assuming that if the windows are that small, that if somebody's standing close to them, the temperature difference is not felt as significantly because the glass area in the overall assembly area is smaller. So there are some exemptions there. But now notice that this one over here, the UW installed value it's a larger window. Okay, it's 16 square feet, and the UW installed value is greater than the threshold. And so the Passive House planning package automatically flags this as exceeding the comfort criteria. All right, so that's what we looked at there. That's what's going on here. Now you'll find that you can flag this as an exemption for other reasons. The consultant or the designer can do that. No, and we don't have the exemptions slide there. The exemption is this window, it's exceeding the comfort criteria, might be in a location that's not commonly used. Let's say a window in a basement, in a mechanical room where nobody really hangs out there watching movies or anything like that. There are a couple of exceptions, but that's the primary one. It's like, are people going to be spending time there? And again, this goes back to the comfort idea. You want the people living in the building as they normally use it to be comfortable. You're not going to hang out in these little use rooms, so it's not an issue. So in that particular case, the consultant can turn an exemption flag on here and the red box goes away. And so it's all good. Okay, that's window comfort criteria. Let's talk about ventilation. All passive house buildings have to have continuous balanced ventilation. And that's whether it's new construction or a retrofit. Now, in a retrofit, the question is, well, when do you put this in? Especially if you do it in phases. If you tear the building apart and do everything at once, it doesn't matter. But if you do it in phases for whatever reason, you have to be careful about when you put the ventilation in, right? So here's the basic ventilation concept. You'll notice we've got orange and green. The orange is fresh supply air coming in. It's filtered fresh air coming in from outside. And the green air is stale air coming from basically the wet area. That's going to be the bathrooms, the laundry room, the kitchen, and that gets exhausted and that goes out. And for every cubic feet of fresh air you bring in, you exhaust the cubic foot of quote unquote stale air. Okay? That's just the way they work. Now you actually have to put air sources in all the supply rooms and exhaust registers in all the exhaust rooms, but you do not have to put some kind of air source or exhaust source in every room. What we do is we put them in the primary rooms, supplies in living rooms, dining rooms, bedrooms in particular, because we spend 8 to 10 hours a day in the bedroom. And then exhaust, like I said, in the bathrooms, laundry rooms, and kitchen. Hallways, entryways, mechanical rooms, closets, places like that don't need to have a direct supplier exhaust in them. What we count on is that there are openings between different parts of the interior building, and the supply air gets transferred to other parts of the building so that over a period of time, the whole building has fresh air. Okay. And these are pretty low velocity air amounts. And I know from living in a passive house, they're so low you can't feel them, you can't see them, but you do get fresh air throughout the house. It just happens. The way it happens is you do have to make sure you do have some kind of openings. You don't want to, you can't close off, let's say, a bedroom with a really tight air sealed door and assume that that supplier is going to come into that bedroom and escape from that bedroom into the rest of the house. Okay, it's going to build up in there to a certain extent. So you have to think about the transfer zones. Okay, so that's how we approach passive housing: supplies, exhaust, and transfer zones. The ventilation system also has to consider the appliances. First of all, you're building a balloon, so you don't want holes in the building, like with range hoods or gas dryers or things of that sort. You can do that, but you have to make sure that you're not creating intentional holes. So typically what we see are condensing dryers that don't have a vent, recirculating range hoods that don't have a vent. Okay, although personally I like exhausting range hoods, and when I've done my 2 certified passive houses, I put an exhaust hood, but I put dampers in them so they sealed up tightly when not in use. Okay, because again, I want to maintain my balloon. So you have to think about this stuff. When you're retrofitting, you're going to put in ventilation equipment. And the question is, well, where do you put it? In multifamily buildings, which are shown here, you can take and you can put it up on the roof. You know, you can put 1 big unit on the roof, depending on the number of units, or let's say 3 big units. But you have to figure out how to get that supply and exhaust air into the building. Okay, and then supply air into the building, exhaust air out of the building. Do it in such a way that you know, you don't disrupt, that you can do it in the construction sequencing properly, and that you don't really pretty much wreck the interior of the building. You have to put the ducts somewhere. Okay. The other approach is you can put each unit can have their own individual ventilation unit. And sometimes that's done. I've seen both approaches done on multifamily buildings. it depends on a lot of factors. And so you need to get your mechanical engineer involved, have that discussion, talk to your passive house consultant, so on and so forth. Okay. And one thing that comes into play here, which is not shown in this slide, it's shown on this slide. No, it's not. Okay, sorry. It's where do you put the ductwork? And this comes up for the appliances too. The more ductwork you put in a building, the more potential thermal bridges you have, the more energy impact you have. You want your duct runs to be as short as possible and to be insulated. And so that comes into play when we calculate a model for one of these buildings. One of the things we do for the ventilation system is to put in there the length of the ductwork to inside and outside and how well they're insulated. And you can definitely see an impact on the efficiency of the ventilation equipment. And the ventilation equipment has to be at least 75% efficient for the heat exchange, which we haven't talked about yet. And I believe further slide does touch on that. We talked about the methods, okay? We're kind of jumping around here. We've already done this slide. 2 methods, energy demand and building component, and then general criteria, okay? On the energy demand method, you actually build a model, okay? It's similar to new construction, but with relaxed criteria. In the EnerPHit building component method, it's prescriptive. We also have this kind of thing in the California Energy Code. We have performance and prescriptive based methods. So it's similar to that. Prescriptive method here in the EnerPHit world, you have specific R values, U values, and you have to have a ventilation system of at least 75% efficient. This is climate zone dependent. Here are the passive house world climate zones as defined by the Passive House Institute. These are different climate zone definitions from any other organization that I've seen. And for the passive house world, these work just fine. Let's skip that one. Okay, let's see. Here's the criteria in nerdy numbers. Okay, the energy demand method. Notice you have heating and cooling. Okay, those are the specific criteria that you have to hit in the model, the building model that you do. Plus, remember the general criteria of moisture protection, window comfort criteria, airtightness. Okay. In the component method, notice you don't see the word heating or cooling there at all. Instead, you see insulation, paint colors, window UW installed value, solar heat gain coefficient, and so on and so forth. So if you install everything that hits these criteria, then you can certify it as an EnerPHit building. Okay. I think I've covered that. I think I've covered that. Okay. So in the PHPP, remember I said there's a dashboard. So for new construction, this is the dashboard up here. Okay. There's also a dashboard for EnerPHit. Okay, and notice this is the prescriptive approach here. So this is the building envelope criteria, U values and things like that. There's solar heat gain coefficient, so on and so forth. This is the prescriptive criteria. This is the performance approach, but this is no heating or cooling demand criteria. That's not true. I'm seeing heating and cooling demand right here. Okay, so this looks suspiciously like, here we go. Thermal comfort. This is the EnerPHit performance approach. Okay, so this label here is not quite correct. Okay. Oh, here we go with the ventilation system efficiency. That really ought to be in that other location. It just shows 2 different places. Here's your heat recovery ventilation equipment here. Here it's down here, much longer duct runs. Here there's ventless appliances. Here there's vented appliances. All this duct work has to be taken into account. And notice in this particular case, the 84% efficient energy recovery ventilator, which is an acronym, one of 2 acronyms for ventilation equipment, is 84% from the factory. but when you factor in all this duct work, it goes down to 71%. And what happens is these exterior venting equipment also, in addition to the ventilation system, like the dryer and the range hood, get factored into this too. So this is not eligible for component certification. That's the point we're trying to make here. So it matters where you put this stuff. That's the simple message here. And that has to be figured out in advance. Again, probably before you start tearing the building apart. Exemptions. There are exemptions in EnerPHit. There is the criteria that we've talked about, but there are certain cases that certain problem areas that you just might not be able to work around. We have a similar thing in Title 24. There are exemptions in certain cases. Let's say there's an exemption for solar PV installation if the building is just surrounded by too many trees and there's no solar exposure. There are exemptions for historic buildings that are designated historic structures that you cannot modify the outside, at least the visual appearance, so on and so forth. We have a similar thing in the EnerPHit world. Here's a couple of them. Legal requirements. I can't think of a good example of that. Historical building preservation authorities, that's kind of a legal requirement. Cost effectiveness. If in order to insulate the building properly, you have to spend 2 times the budget that you've got available or whatever reason. I'm not quite sure what the effective threshold is. They're kind of like up to the designers and the architects and the developer and the building owner and everybody to determine what's not cost effective and to make a case. Okay. No available components. Let's say in a particular case, you need to have like a fire damper of some kind because the local building code requires it in a multifamily building. And you just can't find one on the market that's available, in our case, the United States, that satisfies the EnerPHit criteria. Okay. So on and so forth. The biggest one, which will show up on the next slide, is the heat transfer coefficient, or the UW install of the window. Okay. So on and so forth. That says other compelling reasons related to construction. Here's one of the compelling reasons. Okay. Remember I mentioned the thermal comfort requirement. Okay. Rooms with prolonged occupancy. This goes back to the window issue. Or maybe the FRSI issue. You could make a case for that, although that's a tough one because FRSI problems introduce mold and moisture and mildew, which you don't want regardless of the use of the room. That's more for window comfort criteria. The one I've seen most is the window comfort criteria where you just can't hit it for whatever reason. The case I'm thinking of is a commercial building. This is a specific case that I'm aware of, where the commercial requirements of the building owner, this was a franchise actually, and the franchise had specific requirements for sizes of windows, locations of windows, and the direction the windows were facing. And they found that regardless of what kind of windows they bought, there were no windows they could buy on the market that would satisfy the window comfort criteria. They were able to get an exemption for that by putting little heating sources directly under the windows, like little strip resistance heaters under the windows. So what would happen is, if it was too cold outside and the comfort criteria was not satisfied, the heaters would turn on and the surface of the windows would rise, and so the comfort criteria would be satisfied. Now that has a penalty on operational energy, but it was something that still worked out. That had to be calculated in the modeling, and it turns out that the additional energy consumption did not turn out to be a problem, and it satisfied the comfort criteria. So if you're looking at EnerPHit and it's a challenging situation, there is some wiggle room above and beyond the specific certification criteria, depending on the circumstance. Okay. And this is, what if we just can't get there? Okay, this is the case of a door threshold that just didn't hit the comfort criteria, and they put the strip heater under there. And you can see that if you do an infrared camera shot of that, that the right at the threshold of that door, the temperature was more than sufficient to satisfy the comfort criteria. Okay. Okay, so that's some of the things we look at. That's by no means. Oh, I see a question from Dorothy. Does a solar array on the roof count as shading? It depends on what world you're talking about. In the Title 24 world, no. That's irrelevant. Okay, it does provide some shading, but Title 24 doesn't really care about that, essentially. In the passive house world, it can count as shading, and in fact, you are supposed to take into account the effect of shading. Okay, on different parts of the building, not just the windows, but all the surfaces. Now, the thing is with solar panels, um, they do cast a shadow, but they are also glass. So they cast a shadow, but they don't really effectively block a huge amount of the solar radiation. Although I've heard there are some solar panels that do that better than others. Uh, so you really don't get a huge benefit from treating those as shading. You can get a little bit of a benefit, but it's not going to be for a huge surface area and it's not going to be a significant benefit. But technically in the passive house world, yes, you can. Hope that answers your question, Dorothy. Okay, the retrofit plan. Now remember, there are two types of certifications, and there are different ways to go about doing a retrofit. Excuse me, just a second, more water. You can do it all at once. You can gut the building on the inside and or the outside to do what you need to do, put it all back together, and boom, you're done. Not everybody can do that. Some people need to do this in a stepped fashion where they do one thing and then maybe they wait 6 months and then they do the next thing. Then they wait and then they, and so on and so forth. There are a lot of reasons why this could need to be done. One could be budget. One could be occupancy issues. One could be availability of required equipment or components or assemblies. For whatever reason, there may be a case where you need to create a step-by-step retrofit plan that lays out how you're going to do these things, in what fashion, in what order, and what things you do at each step, and what your starting point is, and what your finish point is. Okay. And you have to create a detailed plan like shown here that shows the various steps. And when you do this in the certification world for the Passive House Institute, once you do the certain steps that reduce your heating demand by 20%, the building can then be called pre-certified, a pre-certified EnerPHit. Okay. And then what happens is, as the other steps are done, when they're finally done, uh, and the final testing and commissioning is done, then you can be a fully certified EnerPHit. Okay, so you have like a pre-certification, then a final certification. And this could take place over 5 years or 6 years, whatever, it doesn't matter. But if you're going to do that, you have to develop a plan, and part of the certification process includes the middle of the plan and a review by a certified. So this is a little more complicated than just tearing the building apart and putting it back together all in one big step. As part of the analysis, you just basically show what happens at each step. And what we're looking at here is, in this particular case, it's step 2, by changing the windows out and putting in the ventilation system, there was a 26% savings in the energy demand. And so at step 2, you can get your pre-certification. And then at step 3, 4, and 5, you do all the things you say you're going to do, and then you can complete the certification. Now, this is the effect of this from a climate change perspective from these two approaches. All right, there's 4 things shown here. And this is on the left-hand side of the graph, on the vertical axis, you can see this is CO2 emissions saving. And then on the horizontal graph are the number of years. The very bottom, you want to have the minimum CO2 emissions. So at the very bottom, the dark green line is a complete retrofit, all done at the same time. The point of this graph is to show that, well, if you do it all at once, you're going to have the most significant reduction of CO2 emission. That's really the best way to proceed if you can. But if you can't, okay, you've got in the middle, you've got uh, two different types of retrofits, and they definitely both reduce CO2 emissions, but they only do it, in the yellow case, 30%, and in the light green case, 52% over a 50-year time span. So that's better than nothing, but it's not nearly as good. And then at the top, we've got an existing building that doesn't get retrofit. And so this is assuming a global CO2 emission of whatever, you total 709. I'm guessing that's pounds per square foot over 50-year lifespan. Okay. Um, so clearly the best thing to do is a total retrofit all in one step, if you can, from this perspective. Okay. That's kind of it in the EnerPHit world. That's the introduction. Now let's talk about the pilots. These are other things that are being done in the EnerPHit world. The first one is something called outfit, catchy name. Basically, what they're doing is they're taking prefabricated components and putting them on the outside of a building while people are living in the building. Hence the name outfit. Okay. And what they're trying to do is, and like the EnerPHit pilot that they did 15 years ago, they're trying to determine if they can take this approach and achieve the EnerPHit standard. Okay. And so it's in a pilot phase. In order to do this, you have to do analysis that contains all this stuff. You have to look at the thermal bridges. You have to look at you have to do a dummy building test calculation, which is basically a building model in the passive house planning package. You have to describe how you're going to make it airtight. You have to talk about the embodied energy of the components, which is something that doesn't come up in the new construction or EnerPHit world, although people are starting to pay attention to embodied energy. You have to write a user manual and inhabitant introduction so that while people are living in this building, you're going to explain to them, this is what we're going to do. This is how it's going to affect you. Please don't be alarmed, that kind of thing. And then you have to talk about your shading concept and how you're going to mitigate your thermal breach. You have to write all this up. This is part of the process. And then to implement this, what they actually do is in some cases, they pull off parts of the building on the outside, or in other cases, they just start attaching stuff to the outside. And on the left, you can see a couple of different ducting system approaches here, okay, where they're putting in ventilation equipment, and maybe it might be heating and cooling equipment too, up on the roof, and then they're ducting it on the outside of the building, which is pretty clever. Okay, now remember this ductwork, you want to make it as short as possible, but it also should be insulated as well. So as part of the evaluation of this approach, you have to figure out, well, where the ducts go, how much are they going to be insulated, what are the flow rates, how are you going to get the air into the apartments, and how are you going to make sure that the duct losses are as minimal as possible. Okay, and this just shows some conceptual pictures of a couple of different ways you can run your ducts. I have no idea what this thing is down here. I think this is a ground source heat pump of some kind. That's my guess. Okay. As part of this, you being the implementer of an outfit project, you're also encouraged to do all this stuff too. Do a step-by-step retrofit concept, a renewable energy system implementation of some kind, service solutions, maintenance services, a PHPP calculation, funding application services, quality assurance services, monitoring, all these things. So it's sort of like, it's one thing to describe and figure out what you're going to do to the building, but they also want you to figure out how this building is going to operate or perform and be taken care of once this outfit is done. Like I said, it's a pilot. There are 2 finished pilots in Europe. Here's one in Paris. Here's one in Neotoa, which I believe is in one of the Scandinavian countries, from judging from this description right here, but I have no idea which one. That's finished. Some of the rest of these are either in the planning phase or the construction phase. We have none of these in North America, and we need one. We'd like to have one. We do have panel manufacturers in North America that are probably capable of this, but this is like a new area that people are just starting to figure out. And it is much easier to go in and wrap a house in stuff and not disrupt the occupants than it is to gut the building. From It's easier from some perspective. All right. I did actually see a couple of years ago, I saw a presentation about somebody considering doing this in the United States, but it was an evaluation of a possible approach. And I don't think anything ever came of it. I'm not quite sure. I haven't seen any mention of it since. Dorothy, point of confusion. Wouldn't just adding rooftop solar already reduce the energy demand by 20% and qualify the project for pre-certification? No, it would reduce the source energy, which is different from the energy demand. The energy demand is the amount of energy consumed by the building to heating and cooling. Okay, so that's different. Remember, if you remember the metrics, there's heating demand, a cooling demand, uh, an airtightness demand or requirement, and a primary energy requirement. The primary energy requirement would get reduced by the solar array, but it wouldn't have any effect on the heating demand or the cooling demand because the amount of energy required to heat and cool the building would not be changed at all. Oh, there we go. Alareza, I hope I said that correctly. The world's largest residential passive house EnerPHit retrofit, city of Hamilton. So we've got one in North America anyway. Um, I wasn't aware of that one. I'm going to have to take a look at that one and have to get the folks who do these slides to add that one in. That's great. Thank you. And I hope that answered your question, Dorothy. Good question. Okay, the EnerPHit partial. This is the other pilot. They're actually looking at people who want to retrofit their apartment to passive house standards, but they're in an apartment building or a condo building or a townhouse development or something, and they have no control over the rest of the building. Okay. And they're starting to look at this. Okay. And what they're doing is they basically say, well, you do it to the component method as best you can. But there's some wiggle room here on the airtightness requirement. That's measured differently because you need to take out the factor of connections between this apartment and adjacent buildings, because again, you have very little control over that. There's some things you might be able to do, but you probably can't hit all the surfaces and seal things up that tightly. The primary energy demand, if you're heating, cooling, ventilation, hot water, all of these things are provided by multi-unit equipment, you have no control over your primary energy demand. Okay, this is the amount of energy consumed in order to heat and cool the buildings, going back to your question, Dorothy. In this case, what we do is we look at, well, sometime in the future, the building is going to have to replace these services and they're going to replace them with energy efficient heat pumps. Okay, so we assume that's going to happen. So we assume that that equipment will be what will be powering this unit at some point in the future. And so that's what we look at in terms of mechanical equipment. Okay. This is in the really, really early stages. I know of nothing like this in North America at all. Although Alareza, if you know something, since you seem to be very well informed about this stuff, feel free, throw something in the chat there. If you know somebody that wants to do this, engage a certifier, you can contact me, and then we coordinate with the Passive House Institute. We would love to see something like this in California and an outfit in California too, or multiple of both of these pilots. But because they're pilots, they're not fully defined and all the details have not been nailed down. That's why they're pilots, because there's an exploration involved. Okay. All right. So that's the nerdy stuff. That's sort of like what EnerPHit is all about. Hopefully that at least gives you a good introduction. So I see we've got about 25 minutes left. Is that right, Sarah? 30 minutes, something like that?
We have 35 minutes.
Okay, good. All right, good. Plenty of time for case studies. Okay, going to do 3 case studies. Thank you, Bob. Unfortunately, these are all from the East Coast because those are really the only certified EnerPHits we've got in the United States. Well, actually, one of these is in Canada. So we don't have many of these. We need these. We should be doing that. So hopefully, once you're done here, you will go forth and look at projects that are actually EnerPHitable, if that's a word, and you'll go and make that happen. Okay. First one is going to be masonry. We don't have a lot of masonry here in California. Second one is wood frame. This is most typical of our single family residential construction anyway. And the third one is concrete frame and masonry. We have concrete frame construction here for larger buildings. I'm not sure about concrete frame and masonry again. We're in a seismic part of the world, kind of sorted, depending on where you are. So I'm not sure we have a whole lot of that type of construction. Okay. But anyway, good examples with different challenges. Masonry. This is in New York. This is in Brooklyn in New York. And it's masonry, as you can see on the right-hand side. And in this case, they do a lot of this stuff in New York. I'm saying well, I'm getting ahead of myself. They're architectural firms and construction firms and tradespeople and specialties that just do passive house retrofits of masonry buildings in New York. This is a real specialty there, and there's a lot of activity in this area. Now, there are not thousands of these being done because it's expensive. There's a lot of work involved, and there are only so many people that know how to do this. But we're seeing a trend there. So there are at least several dozen of these in the New York area that I'm aware of. Okay. If you do a gut renovation, it's the easiest way to approach this. Okay. And these are old buildings. These are 200 years old. And as you can see from the brick, they have a tendency to start falling apart at some point. This is what this row house looks like when it's done. Okay. And this is a rendering of the final building. The red band is the thermal envelope. This is the insulation layer and probably the airtightness layer as well. They actually retrofitted all 4 floors and they dug out the basement to make it usable head height space as well. So it's essentially 5 floors. And then they put a little addition on the back as well. And so all of this was part of the EnerPHit process. Their target R values were the floor slab in the basement was R20. The walls were R20, which seemed kind of low, but I'll explain that. The roof was R50 to 70, depending on where it was. And the windows, the UW installed value was a 0.14. Alareza Projects, Passive House Canada, Maison Passive House Canada. Is that there are specific EnerPHits there or outfits, or is this just all the projects in Canada? I would guess it's the latter. For those of you who aren't familiar with what's going on in Canada, there's a lot of passive house activity in Canada. In some ways, there's a lot more there than there is in the United States, depending on how you measure things. So plenty of stuff to look at there. Okay, let's see. All the EnerPHit. Oh, yes.
It looks like Mark has raised his hand.
Oh, okay. Mark, hi, how you doing?
Yeah, good. Yeah, I mean, this is really helpful. Being that there's a lot of money potential soon to come out from the federal to the state of California for some of the residential programs, and some of us have PUC funds. Are there any like no-brainers or just high-level approaches to primarily the envelope retrofits, which it seems like a big hole in terms of what we typically see as part of programs, right? We always switch out equipment and we have the tech program, but in terms of air sealing, is there any kind of, aside from every building being very unique, let's just talk about residential, single family maybe. What are those things that are easiest and hardest to retrofit in terms of air sealing, like sill sealing versus resheathing versus membranes? I mean, I know it's a little detailed, but
Yeah.
any guidance so that we can look into more self-educating ourselves as we evolve our program offerings here in California?
I mean, I think we could do a detailed conversation offline, but let me give you a quick answer, if that's okay, high level. What I've seen for single family, thank you for constraining it to that. That's mostly what I do is residential single family. The biggest problem areas typically are crawl spaces to walls and walls to attic. Couple of reasons for that. Typical California stick frame construction. The attic and the wall intersection is low slope or medium slope, and there's a pinch point right there. Okay. And the only way you have to be able to insulate it adequately, first of all, and you have to be able to air seal it. And the only way you can really do that is to tear off the roof and tear off the finished material on the outside and air seal from the exterior. It's pretty much impossible to air seal it and insulate it properly from the inside. If you tear off the roof, you can get some insulation on the outside, but then you have issues with overhangs if the overhangs are integrated with the framing. Okay, and in cases like that, I tell people just take a chainsaw to your overhangs, cut them off, air seal them, put in new overhangs with a different type of architectural approach. With crawl spaces to sill plates, it's sort of a question of, well, what are you doing with the crawl space? Do you want to turn it into conditioned or in semi-conditioned space and put your air barrier down at grade? Or do you want to put it underneath the floor framing? Wherever you're going to put it, how do you tie that into your air sealing? And then the other question is, are you air sealing from the outside or the inside? From the outside is easier if you're willing to tear off the finished material. And assuming you've got sheathing, I've seen cases where you tear off the stucco and there's no sheathing, there's just paper. If you don't remove the exterior finishes and you do it from the inside, you have to tear off the drywall. And you have that pinch point up at the attic. You have to figure out how to tie your air barrier into the inside. But even harder than that is, how do you build an adequate air barrier on top of a stick frame set of walls? Especially where you have intersections and penetrations that go down in the crawl space or go up into the attic. So it can be a real challenge. The easiest ones I've seen are tear off the outside, put your air barrier on the floor underneath the finished floor, and do the best you can to tie it to the outside air barrier on the sheathing. Chop off the eaves if they're integrated into the framing, remove your roofing, take your air barrier and wrap it up over the roof and back down the other side and tie it into your sill plate and your floor air barrier. And insulate on the outside, insulate on the inside of the roof rafters as best you can. Or you could do insulation on the outside and then insulation at the attic floor if you want, although that's messy and you don't really get much benefit there, even though I know Title 24 likes that approach. And get your air barrier and your thermal barrier in that way. So it kind of depends on whether people are willing to wreck the outside of the building and tear it apart, both the roof and the siding, and what they want to do with the crawl space. So that's kind of an overview, a quick and dirty answer. Those are the challenges, those intersections, and what you're going to do to the building and how you want to deal with those intersections. Those are the real questions. Oh, good. I'm glad that was helpful. And like I said, we can take this offline if you want and talk about more specifics and look at details and stuff. I think we're actually going to have a couple of details here, but none that really address our housing stock too much. Okay. Back to the row house, masonry retrofit row house. This is what it looks like on the outside. They clearly couldn't touch the outside. It's not a historic building, but I think it's in a historic district and they couldn't change the look of the windows. That's a different challenge that I'm not going to talk about, but I know in this case it was a challenge. Here's a couple of examples of things they kind of had to look at. Okay, they insulated from the inside. And going back to, remember, we had those conversations, or I showed you those details about you insulate from the inside or the outside. If you insulate on the inside, your FRSI numbers are going to be lower, and you have a higher moisture, mildew, mold, condensation rate than if you insulate on the outside. But if it's your only choice, it's your only choice. And so you figure out and you deal with it. And this is what they did in this case. They insulated, this is a section, and in the fronts, they insulated more deeply. And I'm not going to talk about the details too much. And on the party walls, they insulated a little bit less. Okay, but they insulated some there. And then they had the typical things you had to deal with. They upgraded the heat pumps, both for hot water and for heating and cooling, ducted heat pump for heating and cooling. And they had to figure out, and they exhausted both of those, all of that stuff. So they had to figure out what to do about that stuff. Same issues that you have on any other building that you're going to make airtight. They pretty much ripped apart the basement, okay, and uncovered all the masonry walls, okay, because all 5 floors were masonry. They dug up the attic and poured in a new slab. I'll show you that in a minute. The problem with the masonry is it was really messy, really, really messy. And their air barrier was going to be on the inside. So their strategy was first to repoint everything where it was needed for structural purposes. That's the guy in the middle. That's what he's doing. Okay. Once they did that, then they went ahead and put an airtight layer of something on there. Okay. I'm not sure what that was. It's airtight stucco-like material. Okay. And that's their air barrier. On the floor in the basement, they poured a new concrete slab and they tied these two together, which we can't see here. Concrete that's at least 4 inches thick is considered an air barrier, although I dispute that depending on the situation. And then in cases where they had structural connections they had to make in corners, like this corner back here, where they had to bolt stuff in, they bolted into the existing masonry, but they had to air seal it. So what they did is after they put the gray stuff on, they drilled for the bolts. They put this black stuff on. This is a technical term. We call it goop. They put black goop on. They put the structural things on. They put the bolts in. They gooped everything on top, behind, everywhere. Okay, so they pretty much sealed the heck out of this whole thing. And that's how they did their wall-to-wall 90 connections. Okay, so I said this is expensive. This is laborious. It's labor intensive. It takes a lot of time. In the basement here, this is where they dug out the basement. Here's the new slab. Since they dug out lower, they had to reinforce the slab. Okay, but they couldn't dig underneath the slab, so they had to reinforce it from the inside. So they built this shelf to reinforce the slab. To reinforce the foundation from the inside. And then they turned that into a feature. All right, like a sitting shelf. And then this is what the structural wall looked like when it was finished, the masonry wall. Okay. This is what the air sealing like on one of the roof sections. They actually used ACX plywood and taped the seams. Plywood can be used as an air barrier if it's properly detailed. So you can mix and match materials any way you can, all right, to get to what you need to get to. And notice they replaced some of the floor joists with open webs, metal trusses. Now, in this case, they would have had to think about thermal boundaries or thermal issues where these trusses hit the outside of the wall, but I'm sure they did that. All right. Here's the air barrier down in the basement. This stuff is Stego. This is also a water barrier and air barrier. And notice they taped all the seams on the bottom here. Okay. And then they taped all the penetration. Okay. You have to worry about that. And then they brought it up to the walls and they tied it into the walls. Now they didn't finish this off. This is not a finished air barrier right here, but they get to that eventually. Okay, they're not showing everything here. And here is that shelf down in the basement right there. They finished it off. Again, air sealed it. Upper floor beams. They had to replace a lot of beams. I don't know if they replaced all of them, but they had to replace a lot. and they were pockets in the masonry walls. Now they couldn't, unless they were going to build a new structural wall inside to hold up all the beams, they had to take the new beams and put them in the existing pocket, which is what they did. In order for that to work, they had to take out the old beams. This is the air and water barrier they used higher up on the interior walls. They didn't use the gray stuff, they used the blue stuff, blue roll-on or spray-on stuff. They had to also use this material on all of the pockets before they put the beams in. Otherwise, there could be air leakage around the beams. Again, painstaking work, beam by beam, both sides. Here's some of those connectors. This is what the finished wall looked like with those nicely gooped connectors there. This is where they're putting a ledger in here. They tied it into some bolts, okay, that were drilled into, this looks more like stone, not masonry. It's not brick, that's for sure. It's big hunks of something, okay. Drilled, they needed to have an air barrier. This in here, this air barrier is this material now. Notice we've got 3 different types of air barriers, well, 4 actually. You know, we've got this stuff, we've got this stuff, we've got this stuff, we've got this stuff. And here, again, here's a pocket of some kind. So they put a different kind of air barrier there, some other stuff. You can use different types of materials as long as they play nicely with each other and they can be tied together. So for this ledger, they had to put their air barrier material behind the ledger before they put the ledger in place. Otherwise, they could have leaks through the bolt holes and through all this masonry stuff that was behind them. And then once they mount that, then they can tie it into everything else. Okay. Painstaking work. Interior insulation, they put metal framing on the inside. Okay. Notice this is what it looks like. Here's the metal framing. There's a gap here. Okay. So they eliminated the thermal bridge from the metal framing through the wall to the outside. Now, this wouldn't have been a significant thermal bridge, but if you can eliminate it completely, why not do that? So they put a layer of insulation here, their metal framing, and then they filled that with insulation as well. And that's how they finished out the inside. So they did steal some square footage on the inside in order to insulate. They had to, it was the only choice they had. And then notice here's the window installation. They insulated between the stone and the window frame. They insulated on the inside and they insulated underneath to separate the window from the stone as much as possible. Now there was a thermal bridge here, but it'd be minor and they would have calculated that. This is some interior insulation. I'm not quite sure what this is. I think they insulated on the floor here. For some reason, that might be down in the basement. This is what they did in the steel framing. Okay, they put a bib surface on it. This is also an air barrier and a vapor barrier, vapor control layer, essentially. And then they blew insulation into it, and then this is what, when you're doing this correctly, you take samples and you measure them for density and weight to make sure that you're getting the proper density, and that's the only way you know you're getting the proper R value. And when you certify a building, you actually have to submit pictures like this that show the thickness of the insulation and the density and things like that to make sure that the R values are correct. Here there's a steel beam, definitely a thermal bridge to the inside. So they covered it up with rigid insulation. They wrapped it in rigid insulation. Then they put plywood layer on it and they wrapped the interior air barrier around the whole thing. So the air barrier here is this membrane, then plywood, seams taped, and they eliminated the thermal bridge to the inside. Okay. So you have to get pretty creative on these kind of retrofits. Here's the window install. This is what I showed. And all of these windows had this potential condition. This is the SI install value, remember, which goes into calculating the UW installed value, which determines whether this window meets the comfort criteria or not. In this case, the SI install value is 0.004. That's the thermal bridge value right here. And that's essentially not a thermal bridge. I mean, it's not 0, but it's so low that you can pretty much, you know, you've mitigated the thermal bridge. This is the window install. Okay, and again, this was done at construction document stage. This is before the building was torn apart. Okay, you need to figure out how you're going to deal with the window install, the materials you're going to use, the thicknesses. You have to calculate the sign install value, and you figure out if your windows are going to perform properly or not. And then this is what it looks like in the field. And you've, again, pictures of the insulation with their thicknesses, pictures of, in this case, this is the window buckets called. This is what it looked like before they cleaned it all up so that they could do the install. So just tearing something like this apart and cleaning it up so that you can do this on, this many windows is a lot of work. Okay, ready for the next 100 years, maybe 200 years. Who's to say? Okay, so that's a brownstone. Like I said, there's lots of people in New York doing this. These are just a couple of examples. These people are all doing multiple projects. They typically only do a couple at a time because these are, from an architectural and construction perspective, these are labor intensive. So I said there's not a lot of resources to do hundreds of these simultaneously. Wood frame, New Jersey, there's a climate zone. Okay, this is the before picture. It's a nice looking house. This is what they wanted to do. They wanted air quality. They wanted reduced energy usage, reduced carbon footprint, reduced maintenance, protecting the house from moisture. These should all sound familiar. Backup power during outage. Okay. Additional comfort and maintaining a 107-year-old charm. Okay, that's a pretty tall order. And this is what the house looks like from the inside. That was the attic shot, I believe. That's quite an attic. I could live in that. Okay. Before construction started, they had to figure out the air barrier. They had to figure out the insulation. They had to figure out the overhangs. They had to figure out the shading. They had to figure out, again, the ventilation and the range hood exhaust and all heat pumps, 100% heat pumps. Now, notice here on the left, you'll see they decided to put insulation on the outside. Okay, that was their approach. And notice this kind of goes back to your question, Mark, here. They pretty much ripped off the whole outside. They did the air and the thermal barrier up the walls, up over the roof, incorporated with the air barrier, then figured out how they were going to do their overhangs as a separate architectural construction. And then they insulated on the interior as well. And they framed in the attic and insulated that too. So it was a combination of exterior and interior insulation. But in order for this to work, they pretty much had to decide they were going to strip the outside. And they also dug up the basement. I'm not quite sure why. I'm guessing because it was unfinished, it was dirt, and they wanted to turn it into conditioned space. And this is what it looked like when they were done. It was 15 mil of air barrier, 2 inches of neoprene graphite insulation, and I'm guessing this is 6 inches of slab. Okay, so they dug it up, put in their finished water barrier, air barrier, and thermal layer all at the same time, and then poured concrete over top of it. And see, they brought their water and air barrier up out of the side to wrap it into their walls. And then this is what the below grade wall looked like. Okay, they insulated on the inside with both a framed wall and unframed 2 inches of insulation. That's to get the thermal break between the framing members and the concrete, and then concrete on the outside too. Okay. On the outside, they air sealed with Henry's VP 100, I believe this is, which is a peel and stick membrane. Okay, there are different products you can use to take this approach. It's just one of them that I'm familiar with. Then they put mineral wool over top of that. I believe it's 6 inches. And then over top of that, they put furring strips. Okay. And then over top of that, they put a new finish material. Now, this is what I commonly see here in California, even for new construction. I'll see they'll build the shell, they'll sheathe it, they'll install the doors and windows. They'll put the air barrier on. They'll do a blower door test before they finish the inside or even rough it in. Then they'll put exterior insulation. Then they'll put furring strips. Then they'll put, oh, here's, I'm sorry. Here's, whoops, here's insulation on the roof section as well. Okay, mineral wool everywhere. This is a close-up of the window install. Again, this should be figured out before you start tearing the building apart. Okay. Exterior, interior insulation, insulated header. Okay, that's a very good thing to do. Here's their UW installed value. Okay, and here's their FRSI, a 0.67. Not a great number, but for this climate zone and this project, it's okay. All right. So this all happens very, very early on. I'm going to skip that part. That's just about heating and cooling loads. I'll just make one comment. Here they did an ACA calculation. For those of you familiar with heating and cooling loads, ACA is sort of like the de facto North American standard. Passive house heating and cooling loads typically come in at about half of ACA load. And I personally think the passive house heating and cooling loads are more accurate. ACA doesn't take into consideration a lot of things that passive house planning package does. So just beware if somebody comes to you with ACA loads, you might want to take a look at the passive house planning package loads and contrast and compare, and then discuss with the mechanical engineer or the mechanical installer. Here's before and after. It looks almost the same. It looks really nice, looks very traditional, all that stuff. One big difference you'll notice is there's no chimney. The chimney is gone. They don't need a fireplace. They don't want a fireplace. In a passive house, you really don't want a fireplace. It has no value. It serves no purpose at all. Okay, finally, multifamily. Ken Sobel Tower, before and after. Looks kind of old and tired on the left. On the right, it looks very modern. This is in Hamilton. Okay. This one is finished, I believe. Okay, Hamilton, Ontario in Canada, our good neighbors to the north. There's a section, there's a vertical section, then a horizontal section. There's elevators, there's trash chutes, there's all kinds of stuff. Same questions though. Where do we insulate, inside or outside? How do we get it airtight? How are we going to provide building services? How are we going to heat it, cool it, and ventilate it? And hot water. The typical walls, they decided to go with an R43 wall, and here they again decided to insulate on the inside and the outside. And so they didn't tear off the outside, they just covered it up. And put in this case, okay, an air barrier and a water barrier combined. And then I think 6 inches of mineral wool. Again, over here, you can see how they did that. Here's what this is like a mock-up. Okay, here's the masonry, whether it's brick or block. Here's dense shield, fireproofing where they needed it for some new sections. Here's an air and water barrier. It looks like either a spray on or a parge coat. Here's their mineral wool. And then here's 2 layers of what's an EFIS system, which is basically an exterior stucco system. Okay. And they put it all together, and this is what it looked like during construction. This is as they were tearing it apart, because in order to do continuous insulation, they had to get rid of things that stuck out or obstructions to that continuous layer. So they had some exterior work to do. And of course, they had to rip up the interior too in order to accommodate this stuff. The windows, they ended up hanging the windows off the exterior masonry. Now, this is kind of interesting. Here you can see they had these L brackets right here, and they set the windows on it. The L brackets are tied into the masonry with Tapcon screws. The windows are set on top of this, and then they insulated underneath the windows. Now, they had to do, this was interesting because your typical steel angles, which is what's normally available in the construction world, had a SI install value of 0.114, which is a thermal bridge. It's really higher than you want. It seriously affects the UW install value of the window. So in this case, they were able to get fiberglass angles instead. Same size, same function, same attachment, but the SI value was lowered to a 0.86. Not great, but better than with steel. Okay. So they figured this all out, and the results from a passive house modeling perspective, the results were satisfactory. Okay. Again, before they tore the building apart, they had to figure this out, really. Down at the ground, this is what they did about the thermal bridging down here. Remember, Mark, I said one of the tough areas is, well, what do you do down at the, the concrete footer at the bottom, or the concrete wall or whatever your grade situation is to the building exterior walls. And this is what they did here. They insulated the heck out of it. This is your mineral wool coming off the wall. They excavated and they put in, it looks like another 8 or 10 inches of insulation, and air sealed it down to the footer. Okay, that's all they could do without really getting radical. Okay, 152 millimeters XPS. XPS is about our 4 to 5 per inch. 152 millimeters is about 6 inches, I believe. So this is about an R20, something like that, right in there. Okay. Up on the roof, they wrapped around the roof and did an R43 roof with a fluid applied membrane and 4 layers of 100 millimeter. So this is 16 inches of R4. Okay. And bigger buildings are interesting when it comes to air sealing. The buildings aren't all ready at once. And so, the crews start working on a certain level and they kind of either work their way up or work their way down, or they have designated sequences that they follow. And you don't want to wait until the whole building is done before doing blower door testing. So in this case, and what's done in many, many places is they did started floor by floor testing, which means that they air sealed an individual floor and tested it for air tightness. And that way they could find leaks and measure what they had and everything else. And they also, and I've seen this on many larger buildings, they also, do air sealing on individual windows. So they will install a window the way it's supposed to be done, and they can test the air tightness of an individual window to see if the windows are up to snuff or if they have issues with the installation details or whatever. So this is very common in larger buildings. I've seen this a lot. And in this particular case, when they were finally done with all this stuff, they hit a 0.2 air changes per hour, which is a really good number, especially for a retrofit. So all of their attention to detail paid off. For ventilation, they had lots of different types of ventilation units depending on the type of building. I'm not going to go into that too much. Again, they had to deal with it. They did a combination of on-roof stuff or stuff in individual floors where they would ventilate multiple units on each floor, common areas, so on and so forth. Much more complicated than a single family. Okay. Heating and cooling, again, more complicated. They had some heat pumps for heating and cooling. And they had some really big heat pumps for ventilation. I'm sorry, not heat pumps, but big ventilation units. Here's their condensing boilers. And here's their, they had rainwater heat recovery, which can really help reduce your hot water loads in colder climates. Not so much in our climate, at least in the bulk of California. Okay. Finished product. Looks good from the inside, looks good from the outside. That's a great finished photo, I think, but taken at just the right time of the day. So next step. If you want to do an EnerPHit, you have to use PHPP, work with a certifier and get a certified consultant or designer. Leverage your community. The passive house community is small, but it's large. Well, it's not large. It's small, but it's generous, so it feels large. Let me put it that way. Takeaways. The emphasis is on resilience, comfort, air quality, durability, low energy consumption, which is a side effect of the first 4 principles. And again, the basic mantra is if you're going to do it right or do it properly. And you can reduce your energy consumption on an existing building by 80 or 90% and build a great indoor building that the occupants are going to love. And if you've ever been in a passive house building, the first thing people say is, "Oh my God, it feels so different. I love it." And that's true, because they're great. So here's a bunch of resources. You'll get the slides where you have all the resources. The one that's not listed here is called Passive House Accelerator .com. They have a bunch of online stuff, webinars, presentations, case studies, everything. So it's an extensive library. Passive House Network, of course, they're listed here under videos, but Passive House Accelerator all has a bunch of videos too. So I would encourage you to go and look at all of these things and go out and build some passive houses or retrofit some passive buildings. Retrofit some buildings to passive house standard. It looks like we've got a few questions if the scroll bar is not flying to me. No, I don't see any questions. Sarah, we've got a couple of minutes, I guess. Yes, no?
Yeah, technically we're 2 minutes over, but
Oh,
if
okay.
anyone has any questions, and Steve, if it's okay with you, we can stay on a few more minutes, but for those
Sure.
that need to hop off, thank you for joining us. We'll get a copy of the slides and the recording in your email in the next couple of days. And feel free to sign off if you need to hop off, but if anyone has any questions, please feel free to put them in the chat or unmute yourself or raise your hand.
Yeah. And thanks very much for your interest in Passive House. Go forth and do some. And thank you all for the good questions too. Yeah, very helpful.
Okay, well, with that, I'm not seeing any questions come through, so I'll go ahead and end it here. So thanks again, Steve, for a great presentation, and thank you all again for joining us.
And thank you, Sarah, for managing everything.
Of
Very
course.
helpful. Always appreciate it.
Okay, thanks all. Bye.
Okay, bye.